So I wanted to do a video, some videos going over the next few modules, and what I'm talking about here first is just an overview of what hypothesis testing is. And hypothesis testing is what we'll be doing for modules 8, 9, and 10, just in slightly different situations related to how many samples we have or what information we have, but the general process of hypothesis testing is the same. So I wanted to spend some time going over that, and then 8, 9, and 10 will seem much more similar, and there won't be as much new material from one module to the next, because you'll see kind of the overall process. So my little example here is, imagine we are trying to decide if Chippy's potato chip company is truthful with their advertising. Their potato chip bags say that the weight of the chips is 14 ounces. We know it is reasonable to assume that there might be a slight variation in weights, but we have reason to believe that they are generally selling bags that are lighter than 14 ounces. We want to take a sample of potato chip bags and see what we find. Okay, so again, as we've talked about, if we could, measure every single bag of potato chips, the whole population, then we would not need any statistics, but we can't do that, so we rely on a sample. So we take a sample of 100 bags and find that our sample mean is 13.8 ounces. Can it be true that the bags actually have a population mean of 14 ounces, but we obtained a sample mean of 13.8? Or does our lower mean tell us that the company must be lying and their bags do not actually have a population mean of 14 ounces? So in other words, what we're saying is, let's say that, our thought right now, or what the company says, is that the population overall has an average weight of 14 ounces, right? Or should be right there at 14. So we got a sample that's lower. Well, we know that if there's a little bit of variation, there's always a chance that just happened that every bag in our sample was less than that 14 ounces, even though the overall population sample would be. So we're saying, how likely is it that we would have gotten a sample mean that low if the population mean really was 14 ounces? And so this is what hypothesis testing helps us to do. Okay, I have my door open and we can hear all these birds, so I'm going to go shut that for just a second. Okay, it'll be a little bit quieter for you to listen now. This is what hypothesis testing helps us to do. It allows us to decide if it's likely or unlikely for a population to have a certain mean or proportion based on what we got for our sample mean or proportion. And remember that generally we don't know what the real population mean is. If we did, we wouldn't need to do this testing. But we have an idea of what it is, or a claim, or something, or maybe in the past this is what it was. And so we're trying to decide if it really still is based on a sample. We can never say that it definitely will or definitely won't happen in terms of getting a certain sample with a certain population mean, because we don't know the population mean. But we can decide that it is likely or unlikely enough to draw a conclusion. So in our example, let's say that our hypothesis testing, which we do with our technology, tells us there's only a 3% chance that I would have had a sample mean that much lower than my population mean, which means that for me, maybe 3% is not likely enough. So I'm going to say there's not much chance that I would have had this sample mean if this is really the population mean. So that tells me that I'm going to assume that this is not the real population mean. Okay. Whether it's likely or unlikely enough is determined by the significance level that we choose ahead of time. You're deciding whether your results are valid by figuring out how likely it is that they could have happened by chance. All right, so overall, we have a few steps to a hypothesis test. We write what we call a null, an alternative, or alternate hypothesis. Those are kind of saying, here's what is thought is true, and here's what I am saying could be true instead. Okay, so for example, something like, the null hypothesis must be that, or would be that the weight of the chip bags is 14 ounces. My alternative hypothesis might be that I think the weight of the chip bags is less than 14 ounces. So I did write alternate here, but usually we say alternative. I mean, they both, okay, but we usually say alternative. We'll decide what kind of test we need to perform, and we'll go over this a lot. This is based on whether I'm talking about means or proportions, whether I have a sample standard deviation or not, and then that tells us whether we use a z-test or a t-test, as we have seen in the past. So we choose what kind of test, and then we carry out the test. We carry out the test with technology. So really at this point, we're just plugging our values into our technology. It will give us some information back, including, like I was talking about, that percentage, how likely is this to have happened? And based on that, we either reject the null hypothesis, so we say, nope, we're just going to say that there's enough evidence to show that 14 ounces is not the correct population mean, or we fail to reject. We do not have enough evidence to throw out that 14 ounces. Okay? And those are the steps. Now I realize it may just seem, really overwhelming right now, but those same steps carry us through the next 3 modules, and we'll go over them quite a bit, and I think it will get to seem much easier. So again, we have our null and alternate or alternative hypothesis, and so the null hypothesis is generally what we kind of accept to be true, what we think is true, what's being assumed. For example, in this case, it would be that the chip bags have a population mean of 14 ounces. We use H for hypothesis, and we put a little 0 there for the null hypothesis. Our alternative hypothesis is that new statement that we're claiming or studying. We put a little a there for alternative. The null hypothesis is always going to have an equals as part of it, so that population mean equals 14 ounces, for example. And the alternative hypothesis will not have an equals. We have our significance level is represented by alpha. So the significance level is the lowest probability for which we will not reject the null hypothesis. Okay, so if my significance level or my alpha is 5%, for example, if our technology gives us back a probability less than 5%, then we reject the alpha. Okay. All right, so how do we decide, again, whether it's likely enough or unlikely? So I'm going to look at option 2 first, and then we'll come back to option 1. So option 2, we use our technology, which will give us something called a test statistic, we'll talk about that in a minute, and a p-value. Okay, so this p-value is important, and we'll talk about this every single example we do for the next 3 modules. The p-value is the probability that the observed results in the study would have occurred by chance rather than due to a specific effect. In other words, this is the probability that I would have gotten that sample value, mean or proportion, even with the null hypothesis value, the assumed population value, being that much different. Okay, and this is what I was talking about before. If the p-value is less than our alpha, then we reject the null hypothesis. There's enough evidence to show that it was incorrect. It's not very likely that I would have gotten the sample data I got and had the null hypothesis true. If the p-value is greater than or equal to our alpha, we fail to reject the null. We say, no, there's a pretty good chance that, if with the population mean being 14 ounces, there's still a pretty good chance that there's a little bit of variation. I could have happened to get a sample that had a sample mean of 13.8. Okay, there's a little saying that can help you remember: if p is low, meaning lower than alpha, the null must go, meaning we reject it. Okay, so if that helps you. If p is lower than alpha, then we have to reject the null. Okay, so that's what we generally do, is we compare our p-value, which the technology gives us, to our alpha, which is either given in the problem, or if it's not given, we assume it to be 5% or 0.05. And so that's, generally how we decide our conclusion. Are we going to keep the null hypothesis and fail to reject it, or are we going to reject it? Now, the other option, I will draw it out in a second and it'll make a little bit more sense, but we have this alpha level, which has a certain probability associated with it. And if we go farther from the mean, the population mean, our probability gets smaller. And if we go closer to the population mean, the probability gets larger. So we can find the z-score that is associated with that alpha level, how far out, how many standard deviations out from our population mean can we go and still, be at that alpha level, okay? So this is called the critical value. And again, I'll draw this out for you in a second. It'll make more sense. So the z-score that goes with our alpha is called the critical value. It's kind of like a boundary. Then we find the test statistic, which uses our sample data. Remember, a z-score, so a test statistic is a z-score or t-score, depending on the situation. And we take the data value minus the mean over the standard error, which is that population standard deviation over n, or the sample standard deviation, over the square root of n. This z-score tells us how many standard deviations away from the population mean our data is. So we have this critical value, which is kind of like a boundary. Then we see where ours falls. If the test statistic is outside the area of the z-score, then we reject the null, otherwise we fail to reject the null. Now, generally, now with our technology and all that, we generally use the alpha and p method. We do not use the critical value and test statistic, but I just want to show you kind of how these go together. So we have our curve, which is either going to be a normal curve or a t-distribution, depending on the situation. And we have our mean here, okay? And then there's some point, whatever our alpha is. So let's say our alpha is 5%, which would be 0.05, okay? That means that somewhere, that's where that boundary is, the probability of it being farther away, of our sample data being farther away from the mean than that point is only 5%. We'll look in a minute and see our graphs here look a little different depending on the situation. But let's say we have it right here, and so this right here, probability is 0.05, okay? This, just like when we were doing the normal curves and we would shade in, this part here, this probability is 0.05. I don't want my p-value, my probability, to come back to me at less than 0.05. So I want it to be here or closer to the mean. So this point right here, whatever this point is like my boundary. That's as far as I can go before my p-value is too small. So this right here is what is known as my critical value. And that critical value is the z-score or t-score that tells how many standard deviations away from this mean do I get to be at this point. So for example, if my critical value is 1.25, that means that this point is 1.25 standard deviations above that assumed population mean. Then I find my test statistic. So my test statistic is the z-score or the t-score, the number of standard deviations where my own sample data is. So imagine that I find my test statistic. So let's say, for example, my critical value is 1.25, okay? If I find my test statistic, and I find that my test statistic takes me up here, and let's say, for example, my test statistic, or z-score, or t-score, for my data is 1.8, Well, then my data, my sample mean, is farther away from the mean than that critical value. That means that its p-value, the p-value here, is the probability of getting this value or even further from the mean. And so in this case, my p-value would be less than that alpha. Maybe my p-value is 0.0003, whatever it is, okay? In that case, I would reject the null hypothesis. And anything past the critical value, this purple part, is what we call the rejection region. So if my data ends up in there, that means it is too far away from this mean. There's not very much chance that I would have this mean be true and have gotten that sample data, so I'm going to reject my null hypothesis in this case. Okay, now let's say we have another example where we have our distribution. Here's our, we're going to say our same critical value and our same p. So let's say, again, it's an example, that the critical value is 1.25, for example, and this p is, oh sorry, not p, this alpha is 0.05. Well, what if now I find my test statistic and my p-value, and if my test statistic, let's say, is here, okay? So now this is my test statistic. Let's say, for example, it is 0.93, okay? Well, that also means that this alpha now, which is all this green part, is going to be, or sorry, I keep saying the wrong thing, that my p-value here is going to be greater than alpha. There's more than a 5% chance. There's more data in here than just that 5%. My test statistic is here. I'm not in the rejection region. I'm even closer to my assumed population mean. So in this case, we fail to reject the null hypothesis. Okay, we don't want to reject it because my p-value is going to be greater than alpha, larger percentage, then we are okay. All right, I'm going to stop this video for now, and I will pick up with a couple of little things and then move into the Module 8 notes.